Hey everybody, this is the video for how to linearize an exponential function. And here we go. So I have some completely made up data here. This is time data and height data. I'm thinking of a lab that I've done before where you analyze the height of the foam from a carbonated drink over time and the height decays exponentially. I wanted this to represent something in real life, but it really is just made up data, and that's not really important. So I have this data, I have uncertainty in my measurements. Let's start by plotting the actual first graph of our dependent variable versus our independent variable. Now, Excel expects us to have our x data, our x-axis data on the left and our y-axis data on the right. So I've written it this way. You should do the same thing. You can copy and paste it so that it is in the correct order. There are other ways to add data to a graph, but I don't want to do that. I want to do it this way. So you should do it this way too. It's easy. So we go to Insert, and then in the Charts section here, there are a lot of different charts. We want this one right here in the bottom middle, an XY scatter plot. And we want the one without any lines. We don't connect the dots. We never do that. We just want the dots. We are going to add a trend line ourselves. So there we have it. I mean, Excel does it. There it is. Let me make this a little bit bigger so we can see it. Let's increase some font sizes here. We should put a title on this. This would maybe be height in centimeters versus time in seconds. If we want to add axis labels, we can click this plus sign and go here to axis titles. Put some axis titles on there. This is height in centimeters. This is time in seconds. Great. Let's add the error bars, right? We have uncertainty in these values. They're not perfect. So we need to put error bars on here. So let's, again, go to the plus sign, select error bars. And we're going to have to click on this button over here and go to more options because they just put standard error bars on there. One of the error amounts is called standard error. I'm not sure what that is. It's something that Excel does by default. But we don't want that. We also don't want a fixed value. We don't want a fixed percent. We don't want to use standard deviation. We want a custom one. And that's good. We have the values already. So, you know, these are our uncertainties are the values for the error bars. We already have them. So horizontal error bar is what's highlighted. And you can see that those are what are highlighted on the graph. So let's specify a value. And our positive. So it is possible for positive error bars, the plus, to be different than the minus, but ours are plus or minus the same value. So we just have to select the same data twice. Our positive error values will be these time uncertainties. Our negative error values will be the same time uncertainties. And then we click OK, and there they are. Now, if we click on some of the vertical error bars and go to custom, we can specify that we want the vertical ones, the height uncertainties, for both the plus and the minus, the positive and the negative. And there we have it, our error bars for all of that. Okay, great. Finally, we want to add a trend line. We could right click. That's how I usually do it. Right click and go to add trend line. You could also still do it from the plus sign, add a trend line. Go to more options. I mean, this doesn't look linear to me. It's not meant to be. It is actually exponential. That's what we'll pick, exponential. I don't know why this is happening to me. I don't know if it's happening to anybody else. When I select a trend line that's not linear, the linear one doesn't go away. So we don't want it there. I can still select it and I can press delete to get rid of it. Let's go back to this trend line. Let's select display equation on chart. So there we have it. And we can embiggen that. And what we should probably do is change the y and the x so that the units work out. Y is height. We don't want to write out the whole word, do we? That'll just G. H for height. And the x-axis is time. Oops. So let's put a T there for time. And we could probably figure out the units here. We want to get centimeters So we need to raise e. I'm not sure this is right. I probably shouldn't put it in a recording and put it on YouTube forever. But I'm going to do it anyway. And if I'm wrong, someone in the comments can tell me. We're going to plug in a number of seconds for t. But I think e raised to a power, that should be unitless, I'm guessing. So to get rid of seconds, we're going to have to multiply it by the inverse of seconds. So we're going to multiply this by seconds to the minus 1 power. That's going to have to be the unit on that parameter. And that gets rid of the seconds, but we need centimeters. So this front parameter maybe is centimeters. So the seconds up here, the seconds to the minus 1 will cancel the seconds from the t, from the time, that you might plug into this formula. The constant e will be raised to that value and be a number, and we'll multiply that number by 10 centimeters to get a height in centimeters. Cool. So that's great. Assuming this was an IA, right? You did an experiment, you collected data, you included uncertainty with your data, you made a really nice graph of it, you plotted the data with error bars, you selected the right trend line, you put the equation of the trend line on, you got, reformatted it so that it made sense for our experiment. Instead of y and x, we have h and t for height and time. We even figured out what the units should be, we think. And we could use this to make a prediction about, how much foam there will be after some other number of seconds or something silly like that. And that's great, but we could be better. The 10 centimeter parameter and the 0.009 seconds to the minus 1 parameter, those have significance. Those are meaningful numbers, and they come from measurements, and those measurements have uncertainty, right? The time and the height measurements. And so the 10 centimeters should have uncertainty, and the 0.009 seconds to the minus 1 should have uncertainty. And I don't know how to get that from this exponential graph. Or if I do, if there is a way to do that, it's just not what we want to do. What we want to do is show off our skills of linearization. Okay, so I'm going to actually make this graph smaller. We don't need this graph anymore. We'll refer back to it maybe. And let's get that font the right size. I'm going to make this bigger just for fun. I don't know why it does that. It got rid of it. It took it out of the exponent. I'm going to put like the caret symbol in here. Maybe I'll put parentheses around this whole thing. The formatting there doesn't look great anymore, but that's okay. We'll refer back to this maybe later on. So how do we linearize this? So this equation, an exponential equation, is written in the form y equals a times e raised to the power kx. So a is a constant parameter, and k is a constant parameter. E is the irrational number e, and y and x are our dependent and independent variables, right? So what can we do here? How can we manipulate this equation so that it ends up being in the form y equals mx plus b? Well, as you know, we can do basically any mathematical function to this equation as long as we do it the same to both sides. And so what we can do here, the trick here is that we can use the natural logarithm, which is a logarithm with a base of e. So when we have e raised to a power and we take the natural log of that, the log base e of that, it kind of gets rid of the e and brings that exponent down out of the exponent. I'm not a math teacher. I'm sure I'm not explaining that very well. Let me tell you what happens here. So if we take the natural log of both sides, and we're going to manipulate our data to do this, we get ln of y equals, and when we take the natural log of that whole thing on the right, the kx comes down out of the exponent, and then we add the natural log of a to that. Right? If you want to learn more about logs, natural logs, you're on YouTube now. Go search on YouTube when you're done with this video. Learn more about how logarithms work and natural logarithms work. They're very interesting. They're very useful. But that is beyond the scope of this video. What we have here is an equation in the form y equals mx plus b. The y is ln y. K is like the m slope. X is x. That's great. And then our plus b is the natural log of a. I hope this all makes sense. So what we're going to do is, instead of plotting height versus time, we're going to plot the natural log of height versus time, which should be a linear function. And the slope of our linear function should be the same as k, which we found to be negative 0.009. And our y-intercept should be the natural log of a. We found a to be 10, and the natural log of 10 is some number. And we'll see that it works out. So this is a walkthrough. If you have this function to linearize, hopefully you've followed along so far, and you can follow along with the next step as well. We only have to take the natural log of our y value. And so I'm just going to make a new column right here and call this ln height. And then we're going to have to figure out the uncertainty in the natural log of our height. So there's a natural log button on your calculator. Excel can do the natural log for us. It's super simple. Equals ln, type it in right. Ln, there it is, returns the natural log of a number, open parentheses. We want the natural log of this number right here, close parentheses. The natural log of 7.73 is 2.04. Great. And let's apply that equation to all of these cells by grabbing this little square and pulling it down. There we go. Those are the natural logs of all of those heights. Great. That was the easy part. The more complicated part is figuring out the uncertainty in the natural log of the height. Basically, what we want to do here is we want to keep the percent uncertainty the same. So if the percent uncertainty in the height was 10%, then we're going to say that the percent uncertainty in the natural log of the height is 10%. It's not 10%. I could have made that up. Maybe I should have. But that's not what I did. And so what we have to do is figure out what's the percent uncertainty here and apply that percent uncertainty here. And here's how we'll do this. We're going to say that on the data booklet, it tells you delta y over y. Well, we're not using an actual equation there, but we're using the idea of percent uncertainty. The uncertainty of a value divided by the value itself is the percent uncertainty. So we're going to say that the delta, the percent uncertainty of ln height divided by the natural log of the height equals, I might be missing parentheses there. I don't really care. Equals the uncertainty in the height divided by the height. I hope that makes sense. If it doesn't make complete sense, you could pause this, you could look it over, you could write this out on a piece of paper, or you could just follow along and trust me. So to figure out the uncertainty in the natural log of the height, the first thing we're going to do is take the uncertainty in the height and divide it by the height. That division there in parentheses is represents the percent uncertainty of the height, and then we want to apply that to by multiplying it by the natural log of the height to get that same percent uncertainty of the natural log. And there it is. Okay, great. And we can grab this little square and pull it down and apply it to the same thing. That's way too much precision, so let's reduce that so it matches the precision of the natural log of the height, and we're great. Okay. Now we should be ready to plot our linearized function. So let's grab the times as our x values. Let's grab the natural logs of the heights as our y values. Insert. Under charts, we go to x, y, scatter. We want the ones without the lines, and there we have it. Whoa. We definitely don't want it that big. That'll get annoying. We can make the font size bigger. Okay. So this is ln of height versus time. Oh yeah. I guess I'm not worried about units here. We can add axis titles. This is ln of height. This is time. The time is definitely in seconds. The natural log of the height, I think, needs to be unitless. It doesn't really matter because we're just trying to get the values of the parameters and the uncertainties in the parameters out of this. So we're less concerned about it. We could add error bars. That would be good. So let's add error bars. We're going to have to do the same process where we tell it to make the values of the error bars a custom value. We want to go over here to error bar options, custom specify value. We're on horizontal error bars, so we will select the uncertainties and the times for both the positive and the negative error value. And then we'll select these vertical ones, custom, specify value. We're going to select these natural log of the height uncertainties for both the positive and negative error values. Okay, great. Finally, we're going to, whoops, clicked the wrong graph. We're going to add a trend line. And we want to get more options on that. I don't know why it's picking different parts of this formatting window. We want trendline options. It's already linear. Linear is always the default. It's obviously the right one here. We want to display the equation on the chart. And there we have it. Well, okay. It's linear. And let's see if we're getting out of this what we are supposed to. So I told you that when we take the natural log of both sides, the slope of our linear function, this k right here, is, right, the slope of our function is k, which is the multiplier in the exponent of the e. So the k is the slope here, but the k is in the exponent here. And in our exponent, we had negative 0.009. And here for our slope, we have negative 0.0086. I mean, that's the same thing, right? And so it looks like we did successfully get our k value, and we'll be able to find the uncertainty in that k value. And 2.3026. So our y-intercept is supposed to be the natural log of a. A is this multiplier out front. We got it to be 10. Let's double check this. The opposite function of taking the natural log of a number is to raise e to that number. So if we have, for instance, equals the natural log of 10, we get 2.3026. And if we do equals, and in Excel to do raising e to an exponent, we type exp, open parentheses. And if we type in 2.3026, 2.3026, that's raising e to the power 2.3026, we get roughly 10, right? And so it looks like we're getting out of this what we are meaning to get out of this. So what was the point? We already had 10. We already had negative 0.009. Remember, the point is that we can get the uncertainties in those values by plotting the maximum fit line and the minimum fit line, which is what we are about to do. Okay, so we're going to find the maximum fit and the minimum fit of our linearized function. I'm happy to do this walkthrough, explain exactly what I'm doing, but to be honest, I'm doing exactly what Chris Donner does in the video that I posted to Classroom. I think he explains it really well. I'm just going to do the same thing. Note ahead of time, and I'll try to mention this again when we're done, the exact way that you calculate the coordinates that we are going to use for these might be different. I have a linear function that has a negative slope. If you had a linear function with a positive slope, the way you do this, like the exact way that you determine the values of the coordinates might be a little bit different, but the idea would be the same. So, as always, think about what you're doing and make sure that what you're doing makes sense. I'm going to get rid of, move that up, and I'm going to get rid of this. And I need a place here to record some stuff when we get there. So, we need to plot the steepest line that fits our data considering the error bars, and we need to plot the least steep line that fits our data considering the error bars. So, you can imagine that these error bars basically make a rectangle, and any coordinate within this rectangle is technically, falls within the uncertainty of this measured value. So our best guess for the time and I guess natural log of the height is that point in the middle, but any point within this rectangle could be the actual value considering the fact that there's uncertainty in our measurements. And so we're going to use that idea to help us figure out what our minimum and maximum fits are. And from that, we'll get the uncertainty in our slope and our y-intercept. Let's do the minimum first. I don't know why. This is what I thought. So to get the minimum slope, we want to go from, in this case, the bottom left corner of this imaginary uncertainty rectangle of our first data point to the top right corner of this imaginary uncertainty rectangle of our last point. And I bet this won't look very good, but I'll try to draw a dotted line. Yeah, that's fine. It's going to be something like that. Right, so how do we find out what this coordinate is? Well, we're going to figure out this coordinate based on the value that we know this center data point is, and then we will manipulate that coordinate with the uncertainty. So for instance, we know that the x value of this bottom left corner is the x value of this coordinate in the middle, and since it's to the left, minus the uncertainty in that x coordinate. I'm going to move this so that I can write out the whole thing. Okay. And the y coordinate of this point is the same as the y coordinate of that data point. And because it's below that data point, it's also going to be minus the uncertainty. Not of the x, though. That's silly. Minus the uncertainty in the y value. Over here, it's just the opposite, right? It is to the right, and it is above this coordinate here. And so the x coordinate will be the x coordinate of this data point plus its uncertainty. And the y coordinate of this top right point will be the y coordinate of this last data point also plus its uncertainty. And so if we figure out what these coordinates are for these 2 points, we can then plot a line that goes directly through those 2 points. The best fit for 2 data points is going to be a straight line that goes between them. So we can write that over here. So let's do the minimum fit and the x and the y. And the 2 points are going to be as follows. It's going to be the x coordinate of this top point is going to be the x coordinate of our first data point minus its uncertainty. And the y coordinate of this first point is going to be the y coordinate of the first data point. Now remember, we're doing equals the y value minus its uncertainty. And make sure we're selecting the natural logs of the heights here, right? You'll find out if you do the wrong thing. Great. That's this data point here. It's 27.7 seconds and 1.88 for the natural log. And we do the same thing or a similar thing for this last data point. So this coordinate here in the top right corner down here is the x value of the last data point plus its uncertainty. And the y value is the y value of the last data point, also plus its uncertainty. And if we select this data and tell Excel to, new thing, we have to add these data points to this same graph. We don't want to make a new graph. I was going here to make a new graph. That's not what we want to do. We want to add this data to this graph. So there's two ways to do this. If we can go home. Let's go to the home. Oh, no, it doesn't matter. Anyway, sorry. We can either click on Chart Design and then click on Select Data, or you can right-click on the graph and go to Select Data. Either way, what we want to do is add a new series. Right? Series 1 is our actual data. We want to add a series. You can give it a name. We'll call it min. The x values are these two x values, and the y values are these two y values. And we'll click OK. And we'll click OK again. And it's hard to see because the drawing is actually, I did a pretty good job of drawing that. There are data points underneath those data points. Let's get rid of what I drew. We don't need that anymore. Delete. There we go. There's a data point in the bottom left corner of the first error box, and there's a coordinate and there's a data point in the top right corner of that one. And now we want to select those, and I'm going to right click and I'm going to select Add Trend Line. Linear is the default, of course, but we want to display that equation. So we'll put it right here. Let's do something so that we don't get things mixed up. Let's make sure this is the min, and let's make sure we know this is like the best fit. And so you can see here the slope could be negative 0.0086, but it could be less steep than that. It could be negative 0.0064. Right? And so that's giving us a sense of what range our slopes could be. Also with the y-intercepts, right? The y-intercept could be as high as 2.3026, or rather the best fit is 2.3026. There's going to be something even higher than that. It could be as low as 2.0553 and still be within the uncertainty. We just have to do this process again for the maximum fit. This is a pain in the butt, but it is the way to do it, and so we do it. So I'm going to walk through this again. If you don't think you need to pay attention to this part to figure out what data point, what coordinates to add data points to and how to do this, I mean, obviously skip ahead, but I'll explain it. So for the steepest line, we want to go from the top right corner of this first point to the bottom left corner of this last point. And that'll be a line that looks like that. So this one, the x coordinate is to the right of this data point and the y coordinate is above. So in this case, we're going to add the uncertainties to both the x and the y. And then down here, this coordinate is to the left of the x coordinate and it's below the y coordinate. So we're going to call this x minus. We're going to take the x value here and subtract its uncertainty. And we'll take the y value of that and also subtract its uncertainty. I said this at the beginning. I want to say it one more time. If you have a linearized graph that maybe has a positive slope instead of a negative slope, you're not going to pick the same coordinates to draw your maximum and minimum fit lines. If you just kind of blindly follow what I'm doing, you won't end up with a good result. So, if your graph isn't exactly the same as mine, the process is, the idea of this process is the same. It just might not be like this exact math might not be the same. And you might not want, in this case, the top right corner to the bottom left corner to get your maximum fit line. So, take this procedure and apply it appropriately to the data that you have. So let's do that. Same thing. We need to get the coordinates of our maximum fit, x and y. And let's do it. The first coordinate up here is our first x plus its uncertainty. And our y is going to be equal to our first y plus its uncertainty. And our final coordinate here, our second coordinate, is going to be equal to the x coordinate of our last data point minus its uncertainty. And our y is going to be equal to the y value minus its uncertainty. And just one thing that I thought of is if you do this right, none of these numbers should be the same number. Right? None of these data points share any values. So just something to look at. If you accidentally typed plus instead of minus on one of these, you might have a data point. One of these numbers here, like this number and this number, might match by accident. So just go back and double check. We have to go through the same process. I'm going to get rid of my drawings again. We don't need them. And we have to do the same process. We have to add these two coordinates to our graph. So we're going to select the graph. Let's go to chart design, select data, add a series, call it max. The x values are these. The y values are these. And there you go. We have a couple of gray coordinates gray data points added to our graph. If we select them and right click, add trend line, linear is by default. Display equation on chart. There we go. Let's embiggen this. And let's label this max. Okay, wonderful. So we can see a range for our slope. Our slope is from negative 0.0064 to negative 0.0114. And our y-intercept is from 2.0553 up to 2.5776. Now, these numbers here from our best fit line are still like the parameters we're going with. These are still, our 10 centimeters and our negative 0.009, seconds to the minus 1. But we're going to use these to find the uncertainty. So let's make a little chart of that. Let's type in the minimum, the maximum, the best. And I'm going to make this column narrower. I'm going to move this chart over. I'm trying to make this so everyone can see it. I got some good feedback on my first one that making the font size bigger would be helpful. And so the uncertainty is here. Okay, so then let's do slope and let's do y-intercept. So I'm just trying to set up a little data table here. So our minimum slope is negative 0.0064. Our maximum slope is negative 0.0114. Our best is negative 0.0086. And our uncertainty is going to be half the range. Half the range from the maximum to the minimum. Here's the range of possible slopes. And so our uncertainty is going to be the maximum value minus the minimum value and then divided by 2. That really probably isn't 0. It's probably just rounded to 0. Let's make that bigger. There we go. It's negative 0.0025. Uncertainty maybe should be an absolute value. It should be, negative 0.0086 plus or minus 0.0025. If we want that to be the case, we can use Excel's absolute value function, which is ABS, open parentheses, and we'll add a close parentheses at the end. And there we have the absolute value of that difference. The minimum y-intercept is 2.0553. The maximum is 2.5776. The best is 2.3026. And that gives our uncertainty half the range equals the maximum value minus the minimum value divided by 2. There we have it. So we now know our best fit slope with uncertainty, and we have our best fit y-intercept with uncertainty. We have just a little bit more to do because the slope, the negative 0.0086 here, is the same as this k parameter up here. And so we can say that this k parameter in our exponential function is negative 0.009 or 0.0086 plus or minus 0.0025. Seems like a lot of uncertainty, but maybe I made up uncertainties that were too big, maybe. I don't know. And so, this number has some meaning, right? This number explains the way that, in this case, what I was thinking of is the way that the foam on top of the liquid decays. This has something to do with, how that happens. And there is some uncertainty to this value. In fact, the uncertainty is 0.0025. We want to know the uncertainty in this 10. This 0.26 is the uncertainty in this 2.3. And this 2.3 is the natural log of the 10. But how do we get the uncertainty in the 10? So it's pretty simple. This 0.26 represents some percent uncertainty of this 2.3026, and we'll figure out the percent uncertainty here and apply that same percent uncertainty to the 10. Right? Percent uncertainty is something that you can apply to values that are, different by a multiple of some number, or in this case, raising something to a power, raising e to the power of 2.3026. So basically what we're going to do is what we did before to figure out the uncertainty in the natural log of the height. Right? And we only need to do this once. There's only one y-intercept value, and so we only need to find the uncertainty of that one value, converting that from what we have here, which is from the natural log, to apply it to the 10. So the percent uncertainty of our y-intercept is the uncertainty in the y-intercept divided by the y-intercept itself, and we want to apply that to this parameter here, this 10 centimeters, right? Because remember, 2.3026 is the natural log of this 10 centimeters. These numbers go together, right? So let's apply that to the 10 centimeters. I'm really just using Excel as a calculator here because it kind of is. And if I hit enter, there we go. So 1.13 is the same percentage of 10 that 0.26 is of 2.3. So now we can say, how do we summarize this? We can say that in our equation that is in the form y equals a times e to the kx, we can say that a is 10 plus or minus 1.13, and the precision should match, and I made up a number that was perfectly 10, which is my bad, so whatever, 10.00 plus or minus 1.13, and the k parameter is negative 0.0086 plus or minus 0.0025. So here's our equation. I'm gonna bring this graph to the front and embiggen it there. So this graph of our dependent variable versus our independent variable was a exponential decay. Excel gave us this equation, and we linearized it. Bring this back to the front. We linearized it. That's this blue line. And when we linearized it, we were able to figure out the minimum slope and the maximum slope, which gave us or allowed us to determine the uncertainties in this 10 and in this 0.009, negative 0.009. And so here they are. And your analysis section would end with this. Your analysis section is going to be your raw data, with some description, your process data with some description, sample calculations with description, your graph with description, your original graph, I mean, like your height versus time, your dependent versus your independent. And then if that's not linear, which yours isn't if you're watching this video, your linearized graph. All of these with description. I want to make sure I emphasize you're not just putting data tables and graphs, you're explaining what they are, explaining anything that stands out about them or is unique about them or interesting about them, whatever. And your analysis section should end with you being able to state the equation that relates your dependent variable to your independent variable. You should be able to say that the relationship between height and time is an exponential relationship with the equation h equals 10 centimeters times e to the power negative 0.009 seconds to the minus 1 times t. And then you can go on to say that the uncertainty in the 10 centimeters is plus or minus 1.13, and the uncertainty in the 0.009 negative is plus or minus 0.0025. Right? That's the end of your analysis section. The beginning of your evaluation section, maybe you restate that kind of, and then you talk about what the significance is of that, right? Can you determine what the 10 centimeters represents about your experiment? Can you explain what the negative 0.009 or 86, what does that represent about your experiment? What does it mean about your experiment that you got the uncertainties that you got? These are like, I don't know, I think pretty, are they big uncertainties? What is this? Equals 1.13 out of 10. So that's 11% uncertainty. Equals 0.0025 out of 0.0086. That's like 30% uncertainty, 29% uncertainty. That's kind of big. Maybe that's something to discuss in your evaluation. Maybe understanding that you had a pretty big uncertainty in that parameter of your equation is part of a discussion of a weakness in your experiment, and that leads you to an explanation of how you can improve that aspect of the experiment so that you could get better results if you were to do this again. I think I'm rambling at this point, so I'm going to be done. I hope that this is a helpful walkthrough so that you can see all of the aspects of this, from plotting your original graph, including error bars and getting the trend line, to manipulating the data so that you can linearize the graph, getting your linear trend line, getting your maximum and minimum fits, getting your slope and y-intercept uncertainties, and then wrapping it all up at the end and seeing how that relates to your equation. So again, I hope this was helpful. If you have any feedback for me, please leave a comment. If you have constructive criticisms for me, that's excellent. I appreciate those. You could be nice about it. And that's it. Good luck on your IA. I'm sure you're going to do a great job. You guys are all working really hard. That's it.